section or chapter 14, section 8, and we're doing part C this time. We've already seen that we can figure out the equilibrium constant, Kc, if we know the concentration of the components at equilibrium, right? The question we've been addressing now is, can we figure out the concentrations of the components at equilibrium if we know Kc, right? So for part A, we said, suppose we know the Kc, and suppose we know some of the equilibrium concentrations, but not all, right? So suppose I'm saying, I'm going to put a box around the things I know. If I know K and I know B, then I can figure out A by isolating A algebraically, right? These two are known. I just plug in what those numbers are and divide them, and now I have A, right? Well, in part B, I use an ice table. How do you spell ice table? That's horrible. Part B, I used an ice table, and I had to figure out, initial change in equilibrium, A, B, C, right? I was given whatever, okay? And I had to figure out these guys by changing, maybe say taking away X and then adding X to that one, right? That was part B. Well, in part C, we're going to do the same thing we did in part B, except this time we're going to simplify some things, and we're going to find an approximation that we can make, all right? So, without getting any further into it, let's suppose that the change that you have is small. And when I say change, I'm talking about, remember our ice table, I, C, E, and let's suppose we've got A in equilibrium with B, and let's say 2B. We've seen that a good bit. And let's suppose that we start out with, 0.1 molar of this and 0 of that. Okay? And let's suppose then that this is going to be adding to X, and this is going to be taking away X, right? Because it's a 2-to-1 ratio. Now, this is what I'm talking about, and this is what Tro means when he's saying suppose X, okay? Suppose that the change is small. And I'm saying, in order to, what do you mean by that, right? Well, really, really small. So one of the negative things about videos is that this is very passive, and so I can't get a guess from you of what is small. But think in your mind, what's a small number? Think in your mind, what's a small number? Do your best. Please don't be passive about this. Okay? Let me choose a small number and see if your number is anything like mine. I'm going to say 6.78 times 10 to the negative 8. Right? You make 6.78. Where'd that come from? That's not really the point. This is the point right here. That's a small number. Okay? So suppose that the change is small, like really, really small. And that's what I mean by change. That's our change right there. What is the approximate value of 0.1 minus some small number? You need to pause the video right now and take a small number and subtract it from 0.1. Subtract a small number from 0.1. Okay, here's what I'm going to do. 0.1 minus 6.78 times 10 to the minus 8 is equal to, and oops, I don't have my calculator with me. Crud. Don't have my calculator. I'm going to do this manually. Watch this. 0.1. I know this is probably too small for you to see. Right? And this is 1, 2, 3, 4, 5, 6, 7, 8. That's how many zeros there are there. 7 zeros. 1, 2, 3, 4, 5, 6, 7 zeros. 6, 7, 8. Okay? I know, this is killing you. 8, that's a 10, 2. This is a 9, 2. This is a 9, 3. This is a 9. Watch this. 9, 9, 9, 9, 9. Rather 0.0. Okay? Can you see that? It's 0.099999322. Now, what is this number? That's what the difference is here, okay? That's that. What is this number to 1 sig fig? It's 0.1. To 2 sig figs, right? It's 0.10. Can you see that when you add a really small number or subtract a really small number from another number, if the difference in magnitude is dramatic, then this becomes negligible. Negligible. So I'm just going to get rid of that. Okay? So we would say it's 0.1 minus 6.78 times 10 to the negative 8 is approximately 0.1. Okay? Now, take that same number, take that same small value, and square it and see what you get. 6.78 times 10 to the negative 8 squared. Okay, I'm going to go get a calculator. You hold right there. Okay, 6.78 times 10 to the minus 8 squared. My calculator is very slow. So that's 4.5968. Where am I here? Equals 4.5968 times 10 to the minus 15. It's another small number, okay? But if I were to say this to 1 sig fig or to say 3 sig figs, I don't just get 0, right? I get 4.6 times 10 to the minus 15 to 2 sig figs, or 5 times 10 to the minus 15 to 1 sig fig. Agreed? 2 sig figs. 1 sig fig. Okay. So my point here is that x can be neglected if it's in an addition problem. If it's in a multiplication problem, it cannot. That's an important point to take away from what we're going to do here in these problems, okay? So what did we assume? The difference between the initial concentration and the final concentration was small. The change was small. We assumed that it had to be small in order to neglect it. How small? Well, it turns out that we're going to, that Tro gives you a criterion, x, which is, this is the change, x over, I'm going to say c. You know what? I'm going to use a c sub I for initial concentration. If that is less than 5%, we can neglect x in addition problems. I know this doesn't make sense yet, okay? It'll make a lot of sense when we start doing it. So if x divided by the initial concentration is very small, we can neglect it in addition problems. What if it's not small enough? If it's not small enough, then in case 1, we have to do quadratics, or solve complicated problems or complicated expressions. Or number 2, we can use approximate value for x to loop it around, okay? This will make some sense. I think our second example, we're going to do this here. I might not make much of it. It's pretty rare that we're going to need it. The only reason I'm discussing it with you is because Tro talks about it. And it's a clever solution. And you want to be exposed to these clever solutions here. You don't want to ignore them. All right, so having said that, let's do a sample problem. So again, we're saying to ourselves, we can skip a quadratic, we can neglect x in addition problems, that's the change, if x over initial concentration is less than 5%. Okay, and I'm going to give you two things to look out for here. All right, so first of all, let's look at this one. This is example 14.12. This is on page 585. And so this is, you've seen questions like this before, right? Consider the reaction for blankety blank, all right? Here's a K, and aha, look at that. That's a small number, 1.67 times 10 to the negative 7. If K, so here's what we got. You know what I'm going to do? I'm going to give myself room here, try to obey these lines. 2 hydrogen sulfide is in equilibrium with 2 moles of hydrogen plus diatomic sulfur. Wow, but that smells bad. Okay, initial change in equilibrium. You've seen this before. Okay, so the initial concentration of this stuff, it's a 0.5 liter. Oh man, we got a more difficult thing to do here, okay? So our moles, 0.0125, and our volume is 0.5, and so our concentration, which is equal to moles per liter, is equal to 0.0125 0.5, so it looks like this is going to be 0.025. I can't. I'm just, my mind is gone right now. I really have to solve that with my calculator. I'm pretty sure that's right, but let's just do that. 0.0125 divided by 0.5. Yep, that's right, 0.025. Okay, so that's the concentration initially of our what? Hydrogen sulfide, okay? 0.025. Find the equilibrium concentrations. All right, 0.025. Oh, and this is 800 and that's 800, so yeah, we're good. In the change, can you see that this is a 2 to 2 to 1? So the change here is going to, I'm going to say minus 2x because these were 0. This is going to be plus 2x. This is going to be plus x. Can you see that? See, the equilibrium concentration is 0.025 minus 2x. This is going to be 2x, and this is going to be x, because it's 0 plus 2x. Okay. Now, I didn't leave myself a lot of room here, so I'm going to use this space up here too. K, these are in concentrations, is going to equal to the concentration of hydrogen gas squared times the concentration of sulfur gas over the concentration of H2S squared, right? So that means that K is equal to, I'm going to use this as my template, 2x squared times x, right? Because there's my x. Can you see this? This is 1. That's 1. Can you see that? This is 2. Here's 2. And here's 3, right? 3. So I'm going to go then. This below it is 0.025 minus 2x. And that's squared, right? Okay, all right. Now look, here's where, this is where it gets magic. You know what? I'm going to give a little blue here to wake you up, just in case you have gone to sleep look at this. Here's x that's not an addition problem, but this is an addition problem, 0.025, and I'm saying, you know what, I have a feeling it's going to be small because it's 0.7. So let's get rid of this. Let's say that is going to be negligible. Let's go back to red. And we're going to go, okay, great, watch this. K is equal to, I'm going to do this part right here. That's 4x squared times x over 0.025 squared. Agreed? Because I got rid of that. Awesome. Okay. So now I'm going to come up here and say 0.025 squared times k is equal to 4x cubed. So x is going to equal the cube root 0.025 squared times k over 4. The cube root, watch this now, be patient, 0.025 squared times k. What was k? 1.67? 67 times 10 to the minus 7 divided by 4. Okay, so this gives us, you know what? I just did this all together. X is equal to 0.0002966. Okay. Now here comes our assumption, and I'm going to change this to blue. This is the whole point of this section. Okay. Here comes the assumption: is x over the initial concentration less than 5%? Okay, so x is 0.0002966, and my initial concentration was 0.025, 0.025. My marker, I'm getting some latency in this marker right now. I'm going to take this and divide it by 0.025, 0.025, and I'm going to get 0.01186. 0.01186, which is 1.186%. Yes, definitely less than 5%. Yes, 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 stars, hearts, blue hearts, I guess, I don't know. Very good, though. So X is, over the initial concentration, is definitely less than 5%. So this assumption is valid. Valid, okay? And so what that means is, let me go back to red now. That means that the final concentrations, because that's what we're looking for, equilibrium concentrations of H2 and S. H2 is going to be 2x. The concentration of H2 is equal to 2x, which is equal to 2 times that number there. Which gives us 0.0005932 molar. And you know what? We're using 3 sig figs here. I think everything's in 3 sig figs. So let's go ahead and say this is 5.93 times 10 to the minus 4 molar. 5.93 times 10 to the minus 4 molar. And let's see, put a big box around that. And the concentration of S2, this was my equilibrium concentration of that, was only X, which is equal to 2 point, where was that number? 2.97. 2.97 times 10 to the minus 4 molar. Love it. Love it. So this was my magic part here, was in the blue. And that's the whole point. In the cases with small equilibrium constant, that's the point. So those are the answers, okay? Now let's do one more example. You might want to, you know what I think I'm going to do? Let's skip the other example for now. Let's say that if we found that this was not 5%, this was not 5, you know what, I'm going to go ahead and do it. You can turn the video off if you like. This is the main point here. All right, I'm going to go ahead and do this other example, but it gets tedious. I know. Especially if you're passive here, it's just killing you right now. If you got a marker out and you're trying to follow along, and you're pausing, that's going to be much better. All right, so let's do another example, and you're not going to like this. I'll warn you now. So suppose that we have, oh no, same reaction. Look at this. It's times 10 to the minus 7. So this is small, right? But now we look at this and it goes, oh, wait a second. So is my initial concentration small. And remember, it's the X over the initial concentration. That was my rule? Okay. So my initial concentration is really small too. I'm not sure that's going to be valid. So let's do the same thing here. I'm going to go a little faster this time. 2H2S is in equilibrium. Somebody's calling, and I don't know who that is. I probably should go and see if it's my wife. You know what I'm going to do that? I'm going to see if it's my wife. Excuse me a second. It was not my wife. Okay, so 2H2 plus S2, all right? Initial change equilibrium. Okay, I'm sorry about the messiness here. It'd be so much prettier if it was prettier, wouldn't it? Initial is 0.5, so my initial concentration, my moles was 1.25 times 10 to the minus 4. My volume was a half a liter, so I had to figure out the concentration myself, which was not nice. All right. What's that? 1.25 times 10 to the minus 4 divided by 0.5 gives me 2.5 times 10 to the minus 4. I guess I should have known that. 2.5 times 10 to the minus 4 is my initial concentration. 2.5 times 10 to the minus 4, okay? And this is 0, and this is 0. Now watch this. If I lose, this is can you see a 2 to 2 to 1 ratio here? So I'm going to be losing here 2x, gaining here 2x, and gaining here, but I'm only gaining x because it's a 1, right? So my equilibrium is going to be 2.5 times 10 to the minus 4 minus 2x, and x. Going a little faster here because we set everything up nicely in the previous slide. So this is going to be 2x squared times x over 2.5 times 10 to the minus 4 minus 2x. And that's the point right here, folks. That is the point right there. The question is this a small, if this is a much smaller number than this, I can neglect it. Okay? But I'm afraid it's not because that's small right now. You see that? All right, so let's do this. Let's suppose we do neglect it. Okay, I think that's what we did last. That's what we're going to do now to test it. We're going to neglect it, and we're going to go, all right, so that means that, let me go back to red here. That means that k, this is about the same as saying k is equal to 4, because that's 2 squared, right? X cubed, because there's 3 x's in there, right? 2.5 times 10 to the minus 4. Okay. 2.5 times 10 to the minus 4 times k is going to equal 4x cubed. So x is going to equal the cube root of 2.5 times 10 to the minus 4 times k, which is 1.67 times 10 to the minus 7 over, oh, this was supposed to be squared. Ooh, I almost missed that. Ooh, I would have been in trouble. Oh, that's even worse. Okay. Times, and divided that by 4, okay? All right, so whatever, if you didn't follow me there, you should work the algebra out. This is algebra which you are expected to be able to do. And I know it's a beast. 2.5 times 10 to the minus 4 squared times 1.67 times 10 to the minus 7 divided by 4 cube root. This gives me 1.377 times 10 to the minus 5. This gives me 1.377 times 10 to the minus 5. Okay, that's what x is. Okay, now here's the magic now. I'm testing it to see if it is smaller than my initial concentration. Or rather, to see if the ratio is less than 5%. 1.377 times 10 to the minus 5. And my initial concentration here was there, here, right? Initial concentration, 2.5 times 10 to the minus 4. And I can see that's not going to be, I don't think this can be less than 5%. Just me here. 2.5 times 10 to the minus 4 equals 0.05507, which is equal to 5.507%, which is not less than 5%. Okay, so we would say that this assumption is not valid. Okay, so what do we do if that's the case? What do we do so what do we do in this case? Well, if that's the case, what I'm going to do is I'm going to take this estimate of x. Okay, so that means this is not correct. Okay, but it's going to be better than 0. I assumed here it was 0, right? So this is a small number. Let's put that back in there. Okay, I'm going to put a little star here and say this is a little esoteric. Okay, so come back to this point here later if you want to understand it deeply. K is equal to 4x cubed, right? See, I'm taking this over here and rewriting it. Okay, this is here. Okay, or rather this one, sorry, not this one. 2.5 times 10 to the minus 4 minus 2. Okay, this x we don't know. I'm going to assume that this is this one here, watch this, times 1.377 times 10 to the minus 5. Can you read that? That's 10 to the minus 5 there. Actually, I'm going to give it to you. This is becoming way too tedious. I'm going to simply say, all right, if this is the case, that's not an x, that's a times. Okay? If this is the case, go ahead and solve for x. Okay? Go ahead and solve for x there, and I will tell you that the fact that we took this estimate for x and used it for that addition problem does make it so we don't have to solve this as a quadratic. It's a third order term, third order polynomial, right? Since it's third order polynomial, we cannot solve this with a quadratic equation. So something like this is going to be really complicated, and this is one way of estimating it, and you'll find that this works. Find that x, and when that's the case, the concentration of H2 is going to be 2x, and the concentration of S2 is going to be x. All right. I know that's going to be a little unsatisfying to you. I will happily work this out with you on request, but I would say that it's a little tedious, and I don't want to drag video watchers through this in a passive manner.